And so now you have all of the basics of being able to send communications, one message at a time, checking off your to-do list one thing at a time. But what if we need to send to, let's say, multiple people, multiple groups, and, we want to do it in an efficient manner? And that's where MPI collectives come into play. And so collectives are basically a way for us to do communications in groups or broadcasting to all at once. And we have different operations that you can use in order to do or send whatever important messages you need to send. All right, and so one of the most basic MPI collective operations is going to be the broadcast operation. Excuse me. And a broadcast, you could think about it as like you're just communicating something to everyone. And it can be like from one manager to all of the other working processes. And so it's kind of like, okay, an analogy is like before I joined, I lectured at Georgia Tech and I taught computer architecture and microprocessor design, and my classes would be like 200 students. For the grading, I would always have, my TAs would have grading parties and I'd order pizza for them. So one example of a broadcast would be the lead TA, letting everyone know these are our options for, lunch, pizza from here or, something, sandwiches from Jason's Deli or something. That's communicating across all needed parties, the information that you need. Okay, that's a broadcast. And so it uses some of the similar components as you have from send and receive, but the introduction of it is you have a special communicator. And the communicator basically defines the group that is going to receive that message. And it can be different types of communication groups. You could have, my TAs for computer architecture versus my TAs for advanced processor design versus a world communicator where everyone gets the message. So there's different ways that we can broadcast what we need. Now, we also have other operations like gather. Like now that everyone knows exactly what the options are, how are they going to let the lead TA know? Like, hey, I want a cheese pizza, or can we get a Hawaiian one up in there? And so in that way, all of the TAs can send their requests back to the lead TA, gathering that information. So you can send a message, similar message, back to that TA, same or similar, okay? And so, gathers can be used to concatenate all of the data together, based off of the rank order and whatnot. And so, and again, you have, the receive count is going to be the number of items that you're going to get from each process and not necessarily that total. And again, it can be based off of the communication group, whether it's just my TAs for computer architecture or for advanced or GPU design. So another thing that you want to consider is that, sometimes maybe some of the messages are not going to be like the same size. And, you need to have, a different, message or amount of data from one process or from one TA than another. And that's when you can use gather V. And so gather V basically means that you can have a variable message link that you receive. And the way that is denoted is that that displacement factor is stored into that. We see that pointer array, DISPLS for displacement. And that's just going to basically specify in the receive buffer the relative displacement based off of each rank in the process. So we have different options that we can use to communicate efficiently. Okay. And like gather, we also have scatter. And so scatter can basically communicate again to different pieces to different groups based off of the segments sent to that process. And so that can also has a variable version as well, where we have a scatter V for sending as well, and scattering that information across our different communication group. And so you see like a lot of the collective operations, they the header for it is going to be very similar with just a little bit of a change. So long as you know the type of operation that you need to do, you'll have all the other pieces that you need. And so we also have reduce operations. And so reduce is if we want to do some type of operation and sum it up across those processes, then we can do a reduction operation. So again, we have the different, it can be like finding the maximum value across all of those processors or performing a global reduction across all of the members within that group. So reduce, you can do different operations, and we'll get into some of the different MPI operations that we can also do. So some predefined operations that you have, you can get the max, min, sum, product, so forth and so on across all of the different messages that you need to receive within your communication group. So this makes it pretty simple to, not necessarily have to go through the rigmarole of figuring out how to send and communicate different messages and different message links. So that's the benefit of our parallel libraries like MPI. And so specific reduce operations like max or min, that will provide you with the returns, the max and min and of those processors and that value within it. You have other different MPI data types that you can use, MPI float for floating int, double int, long int, as well as a pair of ints. So that kind of denotes like the different data types that you're going to receive. And then you have other predefined operations that you can do to create your own operation as well. So, if you want to get into creating your own MPI function and have all kinds of fun, you can do that as well. And so we also have all operations in which we want to have that result of the gather scatter be sent to all of the processes and not to just, the manager or the lead TA. And that's when you can do an all gather where everyone knows everybody else's preferred pizza. If you want to get them a gift later and, get them their favorite pizza, now you know it. And so again, we have scatter and gather as well. So if you want to scatter that information, starting from block J from process I, you can receive the JF block in your receive buffer. And that's going to be able to send distinct data to each receiver as well. And so that's kind of similar to, there's a corresponding all-to-all variable as well that you can use for, variable message length as well. Then we also have a all reduce. So instead of just a reduction, the result is going to appear for all processes and not just to the coordinating process. So again, same typical function header that you use. So long as you know all of the variable components, then you'll be good to go for that as well. Now, we also have what is called a barrier operation. And a barrier is basically allowing for everything to synchronize. What would be, with our example, with our TAs ordering pizza, when would we want to have a barrier operation in that process? So the TA is going to, broadcast the options, everyone decides, and then, everyone needs to make a selection, and that food will then be ordered and delivered. When would be the first probably point in those steps where we might have a barrier operation?
Like once you put the order in, maybe you don't want to get requests after.
Exactly. That would be the first point that I thought of, is that you would have a barrier to make sure you receive an order from every TA or every process. And once you have received it, it's like, okay, now we can make the order, because you don't want to leave anyone out. That's no fun. So, we have different mechanisms that we're able to utilize to coordinate the processes and synchronize. And another point for that would be like, you don't want to, if you're doing calculations, You don't want to return a result when you haven't gotten all of the data back from each process. Okay, and again, we have, lots of documentation, great bedtime reading if you're having trouble going to sleep for you to brush up on. And then also it's, did you talk about like there are different, implementations of MPI? Yeah, we have different, implementations of MPI, Rebecca mentioned that Cray, we have our own version that is from HPE. And then you have, when I worked for IBM, we had our own version. It's not fun when you have to debug the MPI library code on a IBM system either. So, and then there's open MPI. So there are different implementations that you have. And even you are able to create different algorithms to optimize the communications. One of my first research papers in my master's was that we developed an algorithm that would do different versions of all-to-all and all-gather based off of the communication pattern. So, there is a standardized algorithm that you can use, but then there are also different variations that you can use to optimize the communication as well. So it's definitely a whole ever-growing area of research, being able to optimize how processes communicates, because with each architecture and as things become more hierarchical, what an implementation that used to work 5 years ago is not going to work as efficiently on a new architecture. So it's always an ever-growing, ever-changing improvements to the implementations that occur. And we have various tutorials that are available as well. All right, and so now let's continue with, after you finish part one of the practice of implementing the communication, all you're going to do is you're going to incorporate some of the collective communications into that example as well.